Yeah, very good morning to one and all present here in this online webinar. So, so I'm very happy to introduce the resource person with us. He is none other than Dr. Veningston from NIT Srinagar. Sir, we are very happy to host you in this online webinar. So, sir is going to take the session on recurrent neural network and the learning algorithms. So, sir is having high experience in the area of deep learning from the artificial intelligence itself, throughout 15 years or 16 years of his journey. Sir, we are happy to have you, sir. Over to you, Dr. Winston.
Thank you, Dr. Iwin, for having me here as part of this seminar series. Yeah, without any further delay, uh, I'm sharing my screen. I hope it is visible.
Yeah, yes, sir. It is visible. You can go ahead.
Yeah, right, right. Good morning to everyone. Let's get into the topic of the seminar. Uh, it is recurrent neural networks. Okay, so I believe that all the participants, all those who are attending this session, are comfortable with standard fully connected neural network. And then I believe that you will know how to compute the forward pass in the neural network, and also how to compute the how to apply the back propagation algorithm in order to learn the weights of the neural network. Okay, I believe that all the participants have, all the attendees have this prerequisite to proceed with this talk. Right. So basically, the neural network is used to solve a wide variety of classification problems. And most importantly, it has proven its ability, especially in the domain of computer vision, that span across various application domains, starting from agriculture, medicine, and so on and so forth. Okay? Basically, convolutional neural network is widely proven to be a very successful model for working with computer vision applications. On the other hand, we have another family of neural network called recurrent neural network. This recurrent neural network is basically for solving sequence learning problem. So wherever, whatever domain where sequence is a major factor, and recurrent neural network can be predominantly applied there in order to solve problems from the sequence space. Okay, so this is here is the agenda for the seminar. So first, let's see some of the sequence learning problems, and then we'll get intuition behind recurrent neural network, and then we will see how recurrent neural network project pipeline can be defined. And most importantly, we will be discussing about the learning algorithm that is used in the context of recurrent neural network. Okay, I hope all of you are aware that the back propagation algorithm is generally applied in any neural network setting. Here in recurrent neural network, we will be applying the variant of backpropagation algorithm, but it is with respect to some time. So we will see what is backpropagation with respect to time, and that I would probably end the lecture with some discussion on backpropagation algorithm suitable for uh, recurrent neural network. Right. Yeah, a quick recap to what all that you have learned probably in the course structure. From the course structure, I understand that you are
Winston, sir.
comfortable. Yeah,
Hello. Winston,
yeah,
sir. Sorry for interrupting. So we
yeah.
are unable to see the screen. So can you share the screen once?
Is it visible
Ah,
now?
yes, yes. Now it is fine. Yes, thank you.
Okay, fine. Right. So I believe from the course outline, from the curriculum of the course, I hope all the attendees have already gone through the notion of fully connected neural network and convolutional neural network. So one commonality that we observe from both FCNN and CNN is that the size of the input doesn't change. Okay, for example, every instance with which we train a neural network, the size of every instance is actually of same size. Okay, similarly, the input that we use for training the convolutional neural network, once the size of the image is, let's say, said to be 30 cross 30, then all the images in the data set is going to be of same size. Okay, so that both in the case of fully connected neural network or feed forward neural network and convolutional neural network, the size of the input is going to be same. Okay, but of course, these two families of neural networks are used for solving different kinds of classification problem. As you can see here at the right, and here is the feed forward neural network used to assess the health risk of the patients. Probably the health risk could be, let's say, we wanted to diagnose whether the patient is infected with COVID or not, or we want to diagnose whether the patient is infected with heart disease or not, and so on and so forth. Okay, so it could be a two-class classification problem, or it could even be a multi-class classification problem. On the other hand, we use CNN architecture, and what is shown here is a popular lanet architecture, which is also considered the very first algorithm from the convolutional neural network family. But only the outline is given here. It's not completely a lanet architecture, but it looks very similar to it. And most of the other successful CNN model also takes the structure from this lanet, and then but it is proven to be much better compared to lanet in solving various image classification or image recognition tasks. So here now upon giving an image, and we wanted to classify this image to one of these three or four categories. Okay, so here it is very clear that there is apple present in this image, and we want this model, we want the CNN model to assign a high probability value for the category apple, while very less or very less probability is assigned to other classes, so that the model will now decide to assign apple as the label to the image. Okay, this is the way how the neural network is actually trained. And now, once we compute the forward pass, we would initialize the training probably with the random set of weight values assigned to all the weight values involved in the model. And then once we complete the forward pass, then we would get the predictions from the model. And then we would also know the true labels for all the test instances that we will be using for training this neural network. And then we have the prediction and we have the ground truth. And then we have the predicted, and now we can compare these two with the help of the loss function. With the help of loss function, we will get an indicator how much amount of error that the model is making. And once we know that the amount of error that the model is making, then we can back propagate the error to the network all the way down to the initial layer of the network, and then we will be updating the weights. And we will update the weights in a systematic way so that it guarantees that there is some reduction in the loss obtained in the subsequent epochs. Okay, so this is the way how we deal with updating the parameters involved in the model. Right. Uh, Yes, so this is something that I have already emphasized. And then the outputs are actually independent of previous input. For example, the output of the current output of this particular image actually doesn't depend on the previous image on which was applied to the model. Okay, for example, now as model has, let's say, learned something from this image, and now the next sample that comes from the training set is an image of car. And now when it comes into this model, and now model will again learn different set of parameters from this car, which is completely independent of the previous image that was applied to the model. Okay, so outputs no, that is apply that is common to both fully connected neural network as well as CNN. The outputs are completely independent of the previous input, so every input is actually treated independently. Okay, so when X2 was given to this model during the training, and it has no dependence with the previous instance, that is X1, which is probably the patient X1, or the or the training instance X1. Okay, so the subsequent output is going to be completely independent of what is seen in the previous step in the learning process. Right. Let me not get into details, and the slide contains comprehensive details about all that we are discussing here. But due to no limited time availability, and let me probably skip a few slides, which you can probably refer offline, and then you can understand. Okay, so this is the fact. So the outputs are actually independent of the previous, the size of the output actually independent of the previous inputs, because every sample or every instance is actually treated independently in the case of both feed-forward neural network and convolutional neural network. And the other common fact that we observe in both FCNN and CNN is that the input is of fixed length. Okay. So, for example, we decided to, let's say, work with 100 features extracted from every patient in order to make an assessment on health risk. Okay, then all the instances in your data set should contain 100 features. Okay, let's say the size of every input instance is of r power 100, which means it's going to be a vector. It's going to be represented as a vector containing 100 real values. Then all the instances present in the training set supposed to be of same size. So again, as I mentioned in the case of CNN, again, if we use let's say collection of 1,000 images in order to train a classifier which can classify images into one of, let's say, three categories. Okay, now assume that let's roughly have about 300 plus images for every category that we have. So collectively, we have 1,000 images, and all the 1,000 images should be of same size. Even if it is not, and we will have to do some pre-processing in order to make all the images are of same size. But this is something that we need to prepare now while building or while training fully connected neural network and convolutional neural network. Okay. So these two things are common in both standard artificial neural network, which is also called as feed forward neural network, and then even CNN. So even though they are used for solving different classes of problems, but basically both of them try to solve a classification problem. So again, in the context of RNN, we will again be trying to solve some kind of classification problem, but there will be but inputs need not be of same length, and at the same time the output actually depends on the previous input as well. So that is these are the two major differences we observe in the in the case of sequence learning problems. So where RNN could be used in order to solve such class of problems. Okay. Yes. Let's try to understand what sequence learning problem is all about. Okay. For example, you can think of each instance of this image as a neural network, but I'm breaking down into different time slices because no there should be the network is going to be recursively used so as to predict output at various time point. For example, now the input is given to the input no, given to the neural network. You can think of this as the first hidden layer, and then you have the second hidden layer, and then you have the output layer. Okay, so now the task considered here is an auto completion task. Let's say we want to build a system which can help us in auto completion as we let's say type letter D, and we want the system to suggest what could be the character that would possibly be typed by the user. Okay, so you could have noticed the auto completion task in many of the chat applications, right? As you type, it also gives you some suggestions, right? This could be the word, or this could be the next character which you would be interested in typing. Okay, we would also see such a feature in the search engines systems like Google as well. Right now, when a user has typed just D, and then we want the system to suggest us the next possible character that would user type in, and that could be measured in terms of no it could be suggested based on the higher probable character that could appear no immediately after D. Okay. So now, based on that, we want the model to make a prediction on the next character that could be possibly typed after D. So now here the model is predicting that E could probably be the best suited character immediately that comes after D. Okay. Now assume that even user also wanted to type in E itself, and now what could be the next possible character that could follow not just E, that could follow D as well as E. What could follow after D? So we don't independently treat all the previous inputs. We don't want to find out what is the character that could come immediately after E, and we wanted to find out what could be the possible character that could come immediately after seeing DE. Okay, so that's why I say that the output actually does not just depend on the current input, it also depends on the previous inputs. Okay, but in the case of fully connected neural network and convolutional neural network, and the output actually just depends on the current input and it does not depend on the previous inputs. But in the case of sequence learning problems, and we observe a completely new characteristics that every output actually depends on all the previously seen inputs. Okay. Then again, once we find that the next suitable character here is E, and E is most probably appearing immediately after seeing DE. Okay, then again we want to again predict what could be the next suitable or relevant character that could come immediately after seeing DEE, not just seeing E or not just seeing EE, and we wanted to know the probability of the next character that could immediately come after seeing DEE. Okay, so now assume that no system no predict that no P is the right character that the user is trying to user will be likely to type. Right. So here is the auto completion task in terms of character. Okay. So auto completion could even be in terms of word by word. For example, after typing, let's say after user has typed deep, and what could be the next word that user would most likely to type. Okay, you can also build a you can also design a sequence learning problem of this kind, which can probably suggest or recommend and the most suitable words that could possibly come immediately after typing deep. Okay, for example, deep learning or deep dive or deep thinking, okay, whatnot. Okay, there could be many possibilities, and the one which is more likely to appear after deep will be suggested by the model. Okay. Right. And first of all, in order to build an application of auto completion task, an application for auto completion task, and we supposed to represent all the characters in terms of a numeric vector. Okay, for example, here we wanted to recommend character at every time. At every time, we want to predict a character that could most possibly be typed by the user. Okay, that is the task here. So we are not taking the word no auto completion word by word. So we are actually discussing about auto completion character by character. Okay, in this case, now we wanted to give a numeric representation for every character. Okay, and possibly assume that we are designing this auto completion task for English language typing. So we have 26 alphabets in English, and in case you include all the no punctuations and all both the cases, capital case as well as small case, then the number of symbols we have in English alphabet would be more than 26. But for simplicity, let us assume that no, we wanted to build an auto completion task which is insensitive to the uh, case of the typing. Okay, so now here there are 26 characters, so you can give a numeric representation for each character. For example, you can take a vector of length 26, take a vector of length 26, and then the probability mass will be on, let's say this is the representation for character A, so that the probability mass will be completely on A, while keeping zero mass on the remaining characters. Okay, so A, B, C, D, E, and so on and so forth up to Z. Okay, similarly for giving representation for B, then we will define a vector in which probability mass will be 1 on character B, and then for all other remaining characters. So this is how we numerically represent. This is how we numerically represent every character in the English alphabet. Okay, and popularly this way of encoding characters is also called as one-hot encoding. Okay. So nowadays, especially for English word, if you consider the large language models, which are used for which are used for processing and understanding natural text, so they are actually using high dimensional encoding techniques like BERT, Roberta, and all that, because they will have a different representation, because those representations are even meant for capturing the semantics around the words. Okay, so that the size of the encoding of such advanced encoding schemes are going to be embedding schemes are going to be very high. Okay, but here the task is very simple, and we just simply go with this one hot encoding representation for assigning some numeric representation for each no English alphabet. Right, so um, uh, this is how the coding the embeddings for every character looks like. For embedding corresponding to A is going to be like this, and then the embedding corresponding for B is going to be like this, and so on and so forth. Or representation, not embeddings. It's a kind of this is the way how we are going to represent A. So now, as you can see, when we feed, let's say, D into the neural network, and we must know that the size of the no size of the input is actually 26. So the size of, because D is represented as a vector containing 26 values, in which the bit that corresponds to D will have one value, remaining all will have zero value. Okay, so now the input is going to be of 26 size, and even output is also going to be of 26 size. So this is just one kind of sequence learning problem where input and output is of same size. So for example, the output is going to be another character that could possibly be typed after D. So this character's encoding is already decided to have a vector of 26 length, so that now model will make a prediction on what character to type immediately after D. Okay, again, model is going to output another 26 length vector, in which it is going to distribute the probability mass across all the characters. Okay, let's say in this case, model has predicted, let's say E, because model has found that the higher probability mass, let's say 0.6 is the mass assigned to character E, while the remaining 0.4 probability mass is actually distributed across all the rest of the characters. So that since E is assigned with high probability by the model, so that model tend to suggest E as the next character to be possibly typed by the user immediately after E. Okay, now, so this R actually indicates that it is a vector containing, real values. But here, actually, we are going with a binary encoding, so that every value in the vector is going to have values from values either 0 or 1, but in the output space it can have real values, because we are going to map corresponding probability value for each of the characters that could possibly be outputted by the model, so that we generally define, this is the nomenclature we use in order to define this, define the size of the vector used at various part of the network. Right now, after finding E, then again we supply E as input to the model again. So instead of so again further E will further again be given as input to the model, and then the model will be recursively, it will be finding out what could be the next character that model could possibly recommend. Okay, but I have written it in terms of different timestamps. Let's say at time t1, let's say that the model is predicting the next word after seeing one word. At time t2, it will predict the next character after seeing two characters. And at time 3, it will predict next character after seeing three characters. And at time 4, it's going to predict the next character after seeing four characters. And that's what this number denotes. Yeah, there are a lot of examples to follow, but I hope that the problem of auto-completion task no, is a kind of sequence learning task where the output actually don't just depend on the current input, it also depends on all the previously seen inputs. Yeah. So here are the observations from this sequence learning problem. So here the output actually depends on previous inputs also. Okay, for example, this output E of the model does not just depend on the current input, it also depends on the previous input. Okay, so that now the output of every now output at every timestamp should actually depend on the output should actually depend on the inputs that are also seen previously. Okay, so that's where we actually configure a recurrent neural network which looks something like this. Okay, it is not just in case if they are independent, and we need not have this link here, but because output at every time point is actually depending on all the previously seen inputs, so there must be some link with the previous instance of input as well. And at the same time, the length of the input is actually not fixed, because all the words in the English dictionary are not of same length, right? So deep is a word which is made up of four characters. Okay. For example, if you take another word, let's say learning. So learning, the size of the word learning is actually 8 and not 4. So even length of the input can be of different size, and the length of the input is not of same size. So that is another observation from this problem space, especially in the auto completion task. Okay. Probably it is also a kind of classification problem. You can also model this as a classification problem, and you are actually assigning a class label 1 out of 26 characters at every time, right? So after typing D, let us again model this as a classification model. Let us model the auto completion, auto word completion or auto character completion as a kind of classification task. And if you think of it as a classification task, it's actually a 26 classification problem, 26 classification problem, in which you are trying to assign probability value across all the 26 classes, and the one which is more dominant is going to be the one that is going to be recommended or suggested by the system. Okay, out of all the I hope it makes sense. Okay, so at the low level we are trying to solve no we are actually trying to solve a problem of classification in nature. Okay. And it is again a supervised learning task where we would have all the words probably which are widely used in the English literature, and with which we would train this model. Okay, for example, deep is a word that actually present in the dictionary or the training instance. Okay, so we know that after D, possibly E could come, and there could be another word as well, like dip. Okay, even I can also come immediately after D, but probably in our model or in the standard English literature, and most commonly, no, E actually follows D, and I can also come immediately after D, but with less probability. Okay, and so on. This is the way how the model is actually going to learn how to suggest or recommend the next possible character after seeing uh, some set of characters previously. Right. There are other sequence learning problems such as part of speech tagging. So part of speech tagging, you want to assign a part of speech to every word that occurs in a sentence. So here the input is going to be a word, and then you are going to assign the appropriate part of speech tag to this word. So it's again a supervised learning task, and you must have a sentence. So you must have sentence from the English literature, and then you should also have the POS tagging corresponding to each of these sentences. Probably if you have, no, let's say you have 10,000 such sentences along with the POS tagging in your training set, you can safely train a recurrent neural network, which can help you automatically assign or automatically do POS tagging on any given sentence. So because you are training a model with 10,000 10,000 such samples, so that you are expecting model to even replicate this knowledge on assigning POS tagging on completely new sentence, okay, or previously unseen sentence. So this task is again a sequence learning task where the input is not going to be of same size, because there could be a sentence which is made up of 4 words, sentence which is made up of 5 words, 6 words, 7 words, and so on and so forth. And one commonality, one common thing that we observe in the case of part of speech tagging and auto completion task is that both input and output is of same size. Okay, so here input is of same size. Input is of, let's say, certain size R5. So the output is again going to be R5. Okay, but in some sequence learning problems, input and output can be of different size. Okay, much like, but that's not a major factor of concern. Even in the case of fully connected neural network and convolutional neural network, the size of the input and size of the output is not of same size, right? For example, when you assign a label for the image, then yeah, image is of some dimension and the output label is of another dimension. Okay. But here is a good observation that in these two applications, both input and output is of same size, but there are other sequence learning problems where input size, output size actually doesn't depend on the size of the input. Right, and then sentiment classification. See here, so here we are not interested in output at every point. For example, we want to assign a sentiment, being a positive or negative sentiment, to a sentence in English. Let's say here is the review written by the consumers of various no, consumers of electronic products in an e-commerce setting, in a e-commerce setting, where the buyers are actually writing reviews about the products that they have purchased, right? So now the sentence is going to be of different length for sure. The reviews are going to be of different length, written by different users. So it makes sense. And now the output is for every word doesn't require an output. Okay, we don't want to measure or assess the sentiment of the word the, right? So we wanted to finally assign the sentiment score or sentiment polarity after scanning the entire input. Okay, so but still the sentiment does not just depend on the last word in the review, and it also depends on every other words that actually constitute the whole review. Okay, so some no the decision on sentiment should be extracted from all the occurrences of the word, but not in a random fashion. It should be in a sequential fashion. Okay, but the earlier day or olden day sentiment analysis is simply going to it's simply going to find out the number of positive words present in the sentiment, and it will appropriately assign the polarity of the sentiment. Okay, but the recurrent neural network is not going to process the input that way. So it is going to also understand the sequence in which these words are placed. Accordingly, it assigns the sentiment polarity to the review comment. Okay, so it's a good observation that the sentiment value or sentiment class, it's again a two-class classification problem. You assign either a positive sentiment or a negative sentiment to the sentence, and the sentiment does not just depend on the current input, it also depends on all the previously seen words or previously seen inputs. Okay, so here is a quick summary on all the different sequence learning problems we have discussed. In case of text auto completion task, we assign a class to every character in the sequence. While in case of part of speech tagging application, we assign a class to every word in the sequence. Yes, we assign POS a tag for every word that we read from the input. Okay. But in case of auto completion, for every character, we find out what could be the possible next character that could be possibly typed by the user. And in case of sentiment classification task, and we just assign a label, we just assign a class to the entire sentence or the entire sequence of words. Okay, but all of them are sequential in nature. All of them requires a neural network that has the capability to learn some sequence that is present in the input instance. Because sentence or a word in any language follow some sequence, right? So that's why we care about this nature of problem, and we wanted to think about another family of neural network that would have the capability to read and understand the sequence and then predict the output accordingly. Okay, while a fully connected neural network as well as convolutional neural network do not see this type of sequence nature from any input, because if you take an image does not follow any sequence in it. Pixels are randomly scattered across the grid, and then in order to formulate an image, okay, one pixel doesn't depend on the, probably a pixel could depend on the surrounding pixels, but one pixel certainly will not depend on the other pixel which is at the other corner of the image. Okay, that's why sequence learning is not a problem that's widely seen in the images, okay, especially in the field of computer vision. Yes, sequence learning problems are also found on other domains as well. From the speech domain, yes, you wanted to let's say find out the sentiment of the speech. Okay, so speech is a signal which has sequence in it, and now you wanted to assign a sentiment, whether to say that the person is angrily speaking or sadly speaking or happily speaking and so on and so forth. Okay, and then again processing video. So video is a sequence of frames. So every frame is independent, but every pixel in an image is independent, but frames in a video is actually dependent on the previous images. Okay, so because frame is an image in the video, right? Video is made up of sequence of frames, right? So now here we wanted to let's say we wanted to process this video sequence which is made up of sequence of frames, and we wanted to assign the position of this yoga. Let's say this video is about a particular yoga pose, Surya Namaskar, and we wanted to assign this particular label to this video sequence. Okay, there could be another video. You can train a model with set of sequence of videos of different yoga poses, and then you can train a model which can automatically assign a yoga pose for the given video sequence. So here we wanted to label the entire video, not we don't want to label every individual frames, and we wanted to assign a single label for the entire video sequence. Similarly, we want to assign a single label for the entire speech sequence. So these are some of the applications we see from the sequence learning context. And let's now get into the recurrent neural network part. Then we are running out of time. So let me straight away get into the intuition behind the neural network. So let's understand the intuition behind neural network. Okay, yeah, this is something that we have already seen. So we want to ensure that the output at current time point, because output YT stands for output, and output actually depends on all the previous inputs. And also also no, the input can be of different length. Okay, so the model is expected to handle an input of various length. So not necessarily a words in English are of same length, or sentence in English are of same length. They are of different lengths. Words are of different lengths. Similarly, sentences are of different. So that we want model to handle an input of different lengths or varying lengths. Okay? At the same time, we want to ensure that the neural network function that is executed at each time step is of same, right? That's why I have shown you a structure which is very similar to this. And at every time step, we carry out the same set of functions. And that's why these blocks are actually looking very similar to each other, because I don't want to change the function that is to be carried out at every timestamp. No, I wanted to keep the same set of function is being carried out at different time steps. Okay, that is another important, so that no, actually RN actually ensures that we carry out the same functions, which means whatsoever operations we carry out during this time step, the same set of operations are carried out in the next time step as well. Right. So here, yes, W1, W2 stands for weights, which means at every time step, we carry out some learning at various time step, but at every time step, we use the same set of weights used in the neural network. Okay, we basically have two layers of hidden units here. And in the first hidden unit, we use, let's say, W1 weight matrix, and in the second hidden unit, we use W2 weight matrix, and the same weight matrices are going to be used at different time steps. So we are not actually learning different set of weights at different time steps, and we are always learning the same set of weights that is going to be used the number of time steps we run the neural network. Okay, the number of weight values are actually independent of the number of time steps we carry out. Right. Right. So we are able to ensure all these things, and the neural recurrent neural network is a network, so which actually helps us ensure all these uh, points that we wanted to ensure in order to solve a sequence learning problem. Yeah. So here are the slides, which convinces you now how each of these items in the wish list is actually assessed. But I believe that from the discussion so far we had, I hope you are
Yeah, actually, due to poor network, the resource person got disconnected. So wait patiently. So he'll get connected.
Yeah, it's okay now. So I was suddenly out of the meeting. Yeah, let's continue our discussion further. Right. So I believe that all of you are convinced that all the three points we have in our wish list is actually ensured by the neural network that we have thought about. That's basically RNN.
Veningston, sir, sorry for
Yeah,
disturbing.
yeah.
Sir, can you share the screen?
I've already shared the PPT.
Okay,
So
one minute,
you
one
you want
minute.
me to share the screen again?
Yes, yes, yes.
Can you see the screen now?
No,
I'm at slide.
one minute. Ah, yes, now it's fine. Yes.
Oh, oh, oh. So here is the standard structure of recurrent neural network where no, we are going to use three set of weights. Weights, but in case of standard fully connected neural network, we'll have our inputs, input vector, and then we will have some number of units in the hidden layer, and we'll have some a number of neurons in the second hidden layer, and then third hidden layer, and then finally let's have output layer. Okay, this is hidden layer 1, hidden layer 2, and hidden layer 3. Okay, so now depends on the size of the hidden units, which means the number of neurons in the hidden unit. The weight matrix used in that layer is actually decided. Okay, so here we basically have our input right here, and then we use weight matrix U, V, and then uh, W. Okay, so through W, actually the knowledge that the model has gained from the previous input is actually shared with the subsequent time point. Okay, subsequent time step. Right. Say for example, the output of this hidden unit, which means the blue hidden unit, actually depends on U alone, and the output at the current time step is actually depending on V alone, and the output of the next hidden unit, which means output of the hidden unit in the next time step, actually depends on U as well as W. Yeah? U, because W doesn't depend on V, but W depends on U. Okay? So this is how we formulate the function, which is going to be like this. So where xi is the input vector, and then these are all the weight values which are used, and w is the weight value that is indicated here, and then u and v are also the weight matrices which are used in the neural network configuration, and b is the bias. Like any other neural network, every neuron is also attached with a bias, and that bias is what something that is denoted by B here, and C is the number of units that we have in the output. Let's say we are trying to solve a three-class classification problem, so we would have 3 units in the output layer. So that is what going to be the dimension of C. Okay? That's going to be the dimension of C. So now, yes, at every time step, SI, so we are going to compute these things. For example, at time step C, at time step SI, because we are going to repeat computing this function over different time steps. Okay, for example, as you can see from this architecture shown in this slide, there are actually uh, 5 time steps. Okay, T1, T2, T3, T4, and at time step 5, actually we have complete reading the input, and then we have also parallelly assigning them the appropriate part of speech tag. So now SI is going to be computed as sigma, because sigma is the activation function we apply. Say UX. So UAX is the computation we do. It's a linear algebraic computation, linear algebra based computation here. It's a simple no, or the matrix multiplication, right? Or vector multiplication rather, right? So xi is our input, xi is our input, and then let us also examine the dimension of each of these weight vectors which are mentioned here, u, v, and w, right? So we multiply u and xi so as to get the input for all these hidden units. Okay, and then at hidden unit, at hidden unit, no, to compute the uh, you know input to the hidden units, and then w is and then we compute w followed by w is multiplied by what is learned from the previous time step. Okay, so for example, this is time step s, let's say s1. S1 actually depends on s0. So here is a different terminology used in order to denote the time steps. Okay, at time step S1, S1 also depends on S0 through W. So that's why the function includes this portion, and then plus the bias of the bias attached to all the neurons in the layer. Okay. And then we estimate we compute the output yi as the weight vector v multiplied by the current time step s naught s naught, because it doesn't depend on the previous timestamp. Okay, so the computation of output at every timestamp does not depend on the previous timestamp. It depends only on the current timestamp. Okay, that's why yi just depends on si, whereas si is actually depending on si minus one, the time step minus one. Right? And then plus the C. C is the number of classes or number of neuron units we have in the output layer. Okay, in case we are trying to solve, let's say, a three-class classification problem, so C will be three, which means we have three units. So appropriately, we can also estimate, or we can also find out the dimension of various weight matrices which are used in the RNN setting. This is all that we have just discussed. Now, yeah, as we can see here, the size of the dimensions are given here. So the size of x is r n cross 1, because it's going to be an n-dimensional vector. Xi is going to be input is always going to be a an n-dimensional vector, right? In case of auto completion task, in case of auto completion task, so we have represented input as a one hot encoding of size 26, right? So 26 can also be written as 26 into 1, right? So this is the vector I'm talking about. Okay, so that's the dimension of xi, and then the dimension of u is going to be number of hidden units we have. Let's say the number of neurons we have in this hidden unit is d, so that the dimension of u is going to be n into d. Okay, so n is the number of input instances that it is pointing to, and then d is the number of hidden units we have in the hidden layer, so that the dimension of u is going to be r power n cross d. Okay, so this is actually the dimension of d cross n. Sorry, d cross n, not n cross d. So it's actually d cross n. And then similarly the size of the W can be computed as it, because a W is between two hidden units, and we use the same number of hidden units for both the time steps, right? So this architecture doesn't differ time step to time step. So W size of W is going to be, we have D units in the hidden layer, and we again have D units in the hidden layer, so that the W dimension is going to be R power D plus D. Okay. And then the dimension of Si minus 1 is going to be, Si is actually determined by U itself, so that no, the sorry, not U itself, So SI actually depends on previous time step, right? So the dimension of the previous time step is actually again depends on the number of units we have in the hidden layer. So it is denoted by R power D cross 1. So that you can appropriately define once the computation is done, what will be the output of the, what will be the dimension of the output. Similarly, after multiplying these quantity, what will be the dimension of the output. So the dimension of the output here is going to be D cross 1. The output, the dimension of the output here is going to be D cross 1 again. And then, yeah, finally we have D cross 1. So the B is simply the bias units connected to various neurons in the hidden unit. So the size of it is going to be simply R power D cross 1 and so on. And then when it comes to output unit, the dimension of V is going to be, dimension of V is going to be, D units in the hidden unit is actually connected with K units in the output layer. So that the dimension of V is going to be K cross D, and then the size of the current time step is undoubtedly R power D cross 1, and then so C is the number of neurons we have in the, it's very similar to the bias connected to the neurons in the output layer. Okay, so we have C neurons in the, we have K neurons in the output layer, so the size of C is going to be R power K cross 1. Okay, so this is how you can also convince yourself that this algebra operation is compatible with each other. So you can safely perform this operation, and for nonlinearity, you can apply any activation function. Here in this case, it is mentioned as sigmoid. So sigmoid activation is applied here. So in order to learn the nonlinearity present in this representation, and then appropriately, finally, no, we wanted to get the output in terms of a probability distribution. So we would of course use no, sigmoid, softmax. So we would apply softmax at the output in order to evenly distribute, or in order to distribute the probability mass across all the output factors we have. So here is the RNN pipeline. So how can we deploy RNN for solving any kind of sequence learning problem? So first of all, model is something that we have already discussed, and this portion is what constituting the model. And then we need data. As we are trying to solve a classification problem, appropriately you can prepare data as per the task that you are trying to solve. In case of next word prediction, next character prediction, or next word prediction, so you should have no set of sentences or set of words from the standard language library, and then that way you can prepare the data for training the model, and then also precisely specify the task. Okay, whether you wanted to solve auto completion task, or you wanted to solve POS tagging task, or you wanted to solve a sentiment analysis or sentiment classification task, and so on. And then we would use appropriate loss function in order to see how much amount of error that the model is making on the initialized weights. Okay, and loss actually depends on the weight values used in the model. So we would make use of this loss, and we would back propagate this loss on the way to all the weight values in the network, and then we would fine tune the weight value, and that is the task of the learning algorithm. So standard learning algorithm that we use in the context of CNN, as well as in the case of feed-forward neural network, is actually backpropagation algorithm. So can we use the same algorithm even while training the RNN? Yes, certainly we can use backpropagation algorithm for training RNN as well. But since we have many time steps here, so we are going to use a variant of backpropagation, that is something called backpropagation through time, BPTT. So because we carry out some operations in various time steps, and that's why the naive backpropagation is as such used, but it is applied over various time steps. Okay, that is the only difference we see. But as such, algorithm wise, there is no much difference at all. And once no, we learn right set of parameters, by scanning through the input several times in different epochs, and finally we would arrive at the right set of weights assigned to the parameters of the model. Parameters, I mean the weight values. So the parameters of the model are this. These are the parameters of the model, denoted by theta in most of the in the general machine learning world, we refer all the weight values of the model as simply a theta. Okay. Now, once we learn right set of parameters of the model, then that's where we stop the learning, and then we would freeze all the weights for the model, and where we would also witness that there is a reduced loss for this set of weights, so that you can now take the model for deployment. And before that, you can also go for evaluating the model. Also measure the validity of the model by using some standard evaluation metrics. So depends on the task that you are trying to solve using RNN. So here is the generic learning algorithm that you might have even seen in the context of CNN as well as fully connected neural network. So we initialize weights W and B, weights and biases randomly. There are other standard ways of initializing weights as well. We have something called Hay initialization, and then we have another initialization technique called Xavier initialization. So these two are found to be very good in the deep learning context. And then, or you can simply follow some normal distribution way of initializing weights. So you can generate a Gaussian distribution, and then you can appropriately use them as weights for W and B. But however, you can also go with random choice of weight and biases initially for the first iteration or for the first epoch. Okay, and then now iterate over the training data and compute y hat, and y hat is the output of the output at the first time step. Okay, I'm trying to explain this basic learning algorithm in the context of RNN. Okay, so y hat is something that you see right here. So this is what y hat. For example, this is a time step one, so it is going to be y1 hat. This is a time step two, it's going to be y2 hat, and this is time step three, it is going to be y3 hat, and so on up to the number of time steps we are going to execute. Right? And then once we compute the compute y hat, and we are trying to solve a supervised learning problem. So we also know the true label for the training instance. So for all the training instances that we are going to iterate over, for all of them, we know the true label, that is y. And this is something that the model has predicted. Now we can find out the difference between y and y hat by using the loss function. So again, loss function is going to be a function over all the parameters of the model, which means all the parameters, I mean theta, right? The weights and biases of the model. And then we would estimate the loss and what is the amount of error that the model is making compared to the ground truth of all the training instances. And then appropriately, you are going to make use of this function in order to update the weights. So all the weight values are updated as weight minus eta. So eta is the learning rate, and learning rate is also an hyperparameter. So it is good to start with a smaller learning rate, and then you can also try with other choices of learning rate values. But generally, we want a model to learn slowly and steadily, so that we tend to use a very smaller learning rate for the learning algorithm. And then the delta W is what the derivative of the loss function with respect to every weight value in the model. So we are going to compute this, and then yeah. So we are going to compute this, and then we are going to update the. We are going to use this update rule so as to compute the new set of W's and new set of B's for the subsequent epoch. And we are going to repeat it until some condition is satisfied. This condition may be the number of epochs, and you may decide the number of epochs, let's say 200 or 200 or 1000 or 2000 or whatsoever. Or you can also set a threshold of the loss function. And at the moment you see that the loss value is very much close to zero, then that could be an indicator to stop this learning algorithm. And once you stop learning the algorithm, then the right set of weights are learned for the model. And now you can now use it for evaluating the model. And then once you evaluate the model with a test set, and if the accuracy or the output on the test set is promising, then you can now take the model for deployment. Okay, so let me yeah, here are the the dimensions of various weight values involved in the model. That is something that we have already discussed. And here is the overall outline of the learning algorithm in the context of RNN. Okay, so we have weights W, U, and then V. Okay, so W, U, and then V. These are the weight values, and W, U, and V are the vectors, right? Vectors of weights, and there are a lot of weight values inside this vector, lot of weight values inside U, and lot of weight values inside V, and each and every one of them is individually updated by using this update rule. Okay, this delta W11 is actually computed as no derivative of the loss function with respect to W11. And similarly, this portion is computed as derivative of the loss function with respect to, sorry, U12. And this is computed as derivative of the loss function with respect to V13 and so on. Okay, you will have to compute it, and you need not write program for all this. And we have libraries available in Python, and which will do it for us. We just need to mention which learning algorithm that we wanted to use in the RNN setting. You just need to specify the learning algorithm that you wanted to use, no, and then the library will take care of the rest. Okay, but this is how internally the learning algorithm is implemented. Okay, now one thing that we wanted to see finally is we are not using the back propagation as such. We are actually using back propagation through time, right? So here is the notion of time comes in. So we use the same backpropagation algorithm even in the context of RNN, but it is actually through some time unit. Okay, for example, let's say M is the number of training instances you have in your input. So in your input set, let's say X, and the number of training instances you have here is actually M, and we take the summation. We take the average over all the. We take the average of log loss over all the training instances, and then it is also going to be sum up at every time step. Okay, for every sequence, for example, for every sentence, let's say for sentiment classification, so every sentence is going to be of different length, so that length is actually determined by the time step. Okay, maybe the first review maybe of, let's say, 5 words length, a sentence made up of 5 words, so that this time step, this for this instance, 5 time steps will be executed. But in the next review, if it is of, let's say, 15 words, then this time the network is going to be executed for 15 time steps. Okay, so that's how. So we are actually calculating the loss, and we get the average loss, after scanning through the entire training set during the first epoch, or the iteration. So in the first iteration, let's say we examine all the instances in the all the M instances in the training set in order to assess the loss. And here is the simple, the log loss is used. And again, it is a hyperparameter, and you have various choices for loss functions, whichever is convenient for the application that you have at hand, and you can appropriately make a wise choice on the loss function. Okay, so this is the way how loss is estimated, and once the loss is estimated, then you can now make use of this update rule in order to update all the weight values of the recurrent neural network, and you can appropriately fine tune or appropriately learn the weight values. Okay. So this loss function is actually applied between these two. Okay, this is the known output, and this is the predicted output. Okay, you can find out the difference between these two. Okay, you can think of these two as the probability distribution, and you can use the entropy based loss function. This is actually an entropy based loss function here that is written, but I'm not giving you any proof how did I arrive at this loss function, but it is basically entropy based, and which can help you compare two probability and then assign, and also will help you what is the amount of error that the model is making. And you can do it at every time step, and then you can sum up together in order to get the loss for that instance, and then take the average over all the training instances, so that you get the unified loss that the model has made at that epoch. And then now this loss is now going to be back propagated so as to update the weights for the subsequent epoch. Okay, so I'll end the discussion here, and if you have any questions, probably I'm up to take it up.
Yeah. Yeah, thank you, Professor, for your spending your valuable time. So, students, any clarifications or doubt? So you can type your questions in the chat box. Okay, so once again, on behalf of the artificial neural network team, entire team, and on behalf of all the course instructors, I thank once again Dr. Veningston for spending your valuable time with us. Thank you so much, sir.
Thank you, Dr. Ivan, for having me here as part of this seminar series. And I extend my best wishes to all the students who are attending this session. Thank you all.
Yes, thank you. Thank you very much. Thank you.